Okay, so better measures of split optimality, Gini index and cross entropy. Two better measures of split optimalities for classification trees are the Gini index and the cross entropy, which is closely related to the deviance. What's a deviance? They're both based on p hat sub mk, proportion of points in region M from class K, and they both take on very small values if one of the classes has a proportion near 1, and other classes have proportions near 0. So they can both be used to measure node purity. I have no idea what. Okay. I'm so confused. What would a Gini index of a region with 200 data points from class 1 and 400 data points from class 2? So it's a proportion of points in region M from class K. Assume there are only 2 classes. So I'm assuming it's there's 600 data points, right? And class 1 is 200 out of the 600? Region M from class K. So wouldn't it be 1/3? Or it's yeah, 1/3. It has to be 1/3. 2/9? That doesn't make sense to me. First of all, I don't know. Ah, damn. 4/9. 200 over 600 times 400 over plus 2. Oh my god. That's the Gini index? Where's the formula for that? Or am I supposed to read it? Trees that result from recursive binary splitting can get very complicated. In some cases, you may even end up with splits that lead to 2 leaves with the same prediction as shown here. This reflects the difference in the confidence of predictions. For example, in this dataset, among people with a blood pressure greater than 113, 90% of them had heart disease. Jesus. What if I have heart disease? However, among people of a blood pressure less than 113, only 57% of them had heart disease. What? That's weird, man. Yes, yes. This reflects the differences in confidence predictions. For example, this data is among people with blood pressure greater than 113, 90% of them had heart disease. However, among people with a blood pressure less than 113, only 57% had heart disease. So in both cases, having heart disease, yes, was the more common class. But our level of confidence in prediction was much higher for people with higher blood pressure. Okay. I get it. Bigger problem with complicated trees, besides being complicated to interpret, is that they can lead to overfitting to the training data. Interesting. Which can increase the variance, of course. Pruning. We can penalize trees that are too complex. And then we can penalize trees that are more complex. Instead of minimizing the residual sum of squares by itself, we can minimize the residual sum of squares plus alpha times the size of t. Where the size of tree t is measured by the number of leaves. Okay. And alpha is a penalty parameter. Oh. If alpha equals 0, we would just get back to original fully complicated. We can choose alpha by cross-validation. Interesting. Cross-validation? Really? This is some next level shit. This pruning stuff is interesting, man. Sample. Use decision trees to predict whether an object is made of rock or metal based on sonar. Whether an object is made of rock or metal, at least. Oh, okay. All right. I'm gonna have to follow that. Fortunately, I do have the video for this.
The dataset sonarrockmetal.csv contains data on 208 objects.
Okay.
The first 60 columns contain...
This data has 60 columns with only 200 items, really? Damn. Do you really need all that 60 columns?
From sonar readings
Jesus
of
Christ.
The 61st column contains values of R or M.
So, oh, hold on. I'm not going to continue this right now. I'm just going to keep on reading the lecture because I want to know the advantages. Advantages. Easy to easy to interpret and communicate. Resistant to predictor outliers and automatic feature selection. And so, okay. Decision trees have several advantages. They're easy to interpret and communicate, and in particular they model interactions in an intuitive way where one variable only matters if another variable takes on a particular value. Is this Chrono Trigger? Lo-fi hip-hop style? It's kind of cool, actually. I used to like to play that video game. Decision trees are also resistant to outliers and skew. Interesting. Among predictor variables, you don't need to transform predictor variables before analysis. Why is that? It is still a good idea to transform the response variable in a regression problem if it is skewed, so that the prediction made up of the mean from each region are a good representation. So decision trees also perform automatic feature selection. Automatic feature selection? So if a particular variable doesn't contribute much to making a prediction, it doesn't get included. Whoa! How does that work? That means that decision trees are a good choice if you suspect that some of your predictor variables may be pure noise. Yes, because in the Pokemon dataset, there are 2 predictor variables that I think are sus. So what I mean by that is, let's go back to let's see here. We have to go to Kaggle. I think it was SP attack and I'm unranked. I'll be ranked soon, guys. I'll be last place and I'll still be proud of myself because I actually did it. Because the only way is to just go up now. There ain't more down than up, so there ain't no more down if you're last place, so might as well just go up. Okay, I guess I have to like kinda redo the whole bullshit. See, SP attack and SP defense might be correlated a little too high. If I have summary, that's interesting how I didn't even put summary in here. So if I put summary fit, you'll notice that SP attack and SP defense have a higher correlation. I don't get this because SP attack 2 and SP defense 2 is still like, I mean, it's still strongly associated with the predictor variable, whereas this one not much so. That's weird. I think it's because it's dataset, man. Maybe it just happens that we grab the outlier that just makes the p-values less. I mean, we just don't have sufficient evidence to support. Maybe we do. This one definitely doesn't. This one is 0.4. It's not even associated with the fucking predictor variable at all. Binary winner. What is kind of funny though. I mean, Everything else is. It's so weird how SP defense is nothing. Why is that? Huh. Anyways. Perform cross-validation. Cross-validation takes a long time, and then we know we get an 88% power. It's actually a really good indicator that that the logistic regression is actually predicting very well. And then we just simulated a real test. Jigglypuff versus Oddish. If we do that and we predict it, Jigglypuff only has 26%. 27% chance of winning. That's horrible. So Oddish is actually more powerful than Jigglypuff by the dataset standards. All right, decision tree. So, okay, so that's one of the advantages, that you don't have, like, it has feature selection, which is really convenient. It's a little too convenient, in my opinion. I mean, you don't have to use cross-validation for feature selection. It's just as is. I wonder how it works like that. I think you need to know your math to do all that kind of stuff, though. Because I really don't want to get into the statistics portion of it if I don't have to. I may have to, though. Okay. Anyways, let's go back to the lecture. Decision trees have several advantages. It's a good idea to transform the response variable in a regression problem if it's skewed, so that the predictions made up of the mean from each region are a good representation, huh? Decision trees also perform automatic feature selection. Interesting. That means that decision trees are a good choice if you suspect that some of your predictor variables may be pure noise from the perspective of predicting the response. I don't know how that works, but damn, that's really convenient. So one of the limitations of recursive binary splitting is that it's a greedy algorithm. At each step, it just makes the best possible choice for the current step without looking any farther ahead. For example, suppose we have a dataset as shown, with blue X's in the upper right quadrant and lower left quadrant, and red circles in the upper left and the lower right. The greedy algorithm isn't able to pay attention to the fact that if we divide the dataset at x equals 0.5, isn't able to pay attention to the fact that if we decide x, the next step after that is going to be great. Instead, it just makes the best possible choice for the current step, which ends up looking random at x equals 0.3. What the fuck? Really? This means that the regions and the resulting tree of recursive binary split can end up being more complicated than necessary. Sometimes you or a subject matter might be able to interpret the resulting tree and simplify it, but this has to be done on a case-by-case basis. It's more likely that you would want to use a support vector machine for a dataset like this. Yeah. Well, we'll see. There's a reason why that one kernel from this one super genius guy, his accuracy is so high in decision tree is only because of the fact that this model in general in itself is just too easy to interpret. It simplifies things so much, and it's great for like talking to your client in an ad hoc basis, saying, hey, this is what's gonna happen, Jigglypuff is gonna die, you know, or Pikachu's gonna die. But then in reality, it doesn't give you that much of a good result, other than the fact that it uses some random ass shit when it uses decision trees, man. Sometimes you or a subject matter expert might be able to interpret the resulting tree in a simplified way, but this has to be done on a case-by-case basis. It's more likely that you would want to support vector machine. Okay, I already read that. Second limitation. Another limitation of basic decision trees is that the splits are based on single variable at a time. What does that mean? That means they tend not to be very good if the true relationship between predictors and response variable is linear. For example, if the true division between two categories is a diagonal line, we have to approximate that with a series of horizontal and vertical lines. So we end up with more complicated division than necessary. In this situation, linear discriminant analysis or support vector classifier would be a good idea. Dude, I just like, fuck, I cut my lip. Anyways, ew. Oh man, are you fucking kidding me? So another limitation of basic decision trees is that they tend to be sensitive to the changes in the data or in the variables. Huh. That's interesting. I think the next algorithm that we're going to use based upon this classification data is probably a support vector classifier. Support vector machine. So limitation 3, they tend to be sensitive to changes in the data or in the variables included. For example, if the data set shown on the left results in a decision tree shown on the right. Okay, but if we change one data point from being a blue triangle to be a red circle, the decision tree totally changes. This results in high variance, yeah, extremely high. It can result in poor accuracy when predicting new data points. Bagging and boosting are two ways to reduce the effect of this limitation. I have a feeling that we gotta do that eventually. Okay, so summary. Decisions are constructed by partitioning the predictor space into boxes based on one variable at a time. At each step in the construction, we choose the split that provides the greatest reduction of mean squared error, or Gini index, or cross entropy for classification. Gini index or cross entropy, huh? Pruning the decision tree can reduce the variance of the model. Okay. And we use that by cross-validation, right? Depending on the alpha. Okay. Okay. This makes it makes sense. And we're almost there. Alright, so now let's get to the video.
To indicate whether each object is a rock or metal.
Okay.
Here I've already read it.
You know what? I'm gonna just, rather than doing that, I'm just gonna open R. Because I know I have this. Oh, that's weird. I guess I'll just have to follow it along. Okay.
And because this data set did not have a header row, I've used the argument header equals false. Let's set up a training data set consisting of 140 of the objects.
Oh, hold on. Is this a classification or regression? Oh my god, what? Are we predicting anything? What's the predictor variable? What is this data set? What is this horse shit? What? Oh. V6. Okay. This is weird, man. Okay. Alright, we're gonna set that C to 728. Why randomly 728? Why don't I just do 1? Why do they do that? It's like the most randomest thing in the world.
Next, we'd like to use a decision tree to predict whether each object is a rock or metal.
Okay.
We'll do that using the tree function, which is in the tree library.
I'm assuming R means rock. There's a library called tree. Interesting. There's no package called tree. I didn't even install that? That's funny, man. Is it done? I guess it's done.
Syntax of this function contains one argument that's a formula and one object indicating the name of the data frame where we should look for those variables.
This is literally only 8 minutes long.
For my formula, I'm trying to predict V61, that is the 61st column of the data.
Right.
And I'm going to use all of the other variables in the data set as my predictor variables.
This is just like
And
the
finally,
Pokemon one.
we'll look at a summary of the output.
Okay.
Here you can see a list of the variables that were used to construct the tree.
How does that work? How does feature selection work on that? This is magical. This is so black box, it's not even funny, man. Man, I'm so bad.
The number of terminal nodes, or leaves in the tree.
13 leaves in the tree, terminal nodes. Okay, gotcha, fam.
And the misclassification error rate on the training dataset.
That's really good, isn't it? Only 2% error
To
rate?
get a better understanding of the tree, let's plot it.
Ooh. What does pretty mean?
The text function will label each of the nodes to tell us whether we're predicting that node to be a metal or a rock, or for a split, which variable it's splitting on. The argument pretty equals 0 makes the text a little bit easier to read if you have any predictor variables that are categorical.
Okay, so this is categorical variable. This is categorical.
So here's our tree. Next, we can use the predict function to predict whether each object in the validation set is a rock or metal. We'll use type equals class to return the actual predicted response classes, that is, R or M. If we use type equals vector, then it would return the predicted probabilities of being in one of the two classes. Next, we'll create a confusion matrix using the table function as usual.
What? 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 V1 not found. Oh. There we go. There we go. Oh, well, what'd she do? Okay.
So this particular tree has an error rate on the validation set of 7 plus 8 divided by 7 plus 8 plus 13.
So there's an error rate, huh? Error rate would be 7 plus 8 divided by 7 plus 8 plus 34 plus 19. The whole thing, right? 22% error.
4 plus 19, or about 22%. We may be able to improve the error rate by choosing a better number of leaves for the tree and pruning it down.
Yeah, pruning it.
We can do that using...
Because remember last time, what's it called? The terminal nodes has 13 leaves. Yeah, that's a lot, man. This is way too big. This is way too complicated. Look at this shit. 1, 2... Is it really 13? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, there's 13. This feels so black box, it's not even funny. And people get paid $110,000? $160,000 just to do this shit? Why is this so easy? Maybe it's not easy. Maybe I'm making it. Maybe it's way too simplified.
CV.tree to perform tenfold cross-validation.
Okay. There's this thing called CV.tree now? Wow. Okay, so cross-validation tree for regression use prune.tree. Okay. I'm gonna keep that and keep a note for that. Everything feels so black box to me. It's not. not even funny. And I think this is the reason why a lot of people are just only choosing deep learning neural network. Because everyone loves their AI. AI. Everyone loves their deep learning or neural networks.
Choose a number of leaves. Because this is a classification problem, we use the function prune.misclass. If it were a regression problem, we would use prune.tree. Here you can see a summary of the different sizes of tree that were considered, measured based on the number of leaves that they had, the cross-validation error rate, and the value of k, which is analogous to, but not exactly the same as, alpha, which we saw when looking at tree pruning in the slides. We can also plot the error rate as a function of the size of the tree. And you can see that the error rate starts out high, goes down low, and then it may go back up again.
This is cross-valid. That's why is it so easy?
In this case, we can just look at the output to identify the smallest cross-validation error rate. The value of 35 was the third value in the $deviance value, which corresponds to a size of 6. So we could just prune down to a tree with 6 leaves. But just in case you have a very large tree with many possible sizes, it might be a little bit difficult to quickly identify which value that is. In that case, we can look at the minimum value using the min function, and then pick out which elements of the deviance are equal to the minimum. And I've written it this way instead of using the function which.min, so that if there's more than one value of deviance that are all the same and all the minimum, we'll pick that out. And finally, we'll extract which elements of the size value correspond to that smallest level of the error. It's a value of 6, like we saw looking at it by eye. Next, we want to use the prune.misclass function, putting in the tree that we found earlier, and best equal to 6, because 6 was the value we found for the number of leaves that gives the lowest cross-validation error. If this were a regression problem, again, we would be using prune.tree instead of prune.misclass.
How is this so easy, man?
And we'll plot the resulting tree in the same
Wait,
way
how?
we did for the original tree.
So is this tenfold? How is this tenfold? Whoops. What happens if, what if I don't want to do tenfold? What if I want to do 30-fold? Oh, you can just use best... No, that's the tree. Oh. Hold on one sec. This is confusing, man. How do you know... Is there a tree? Oh, you can just specify K. Okay, that's good. Alright. Ugh. Wait, hold on, what?
Instead of prune.misclass.
Text prune.sum equals 0.
And we'll plot the resulting tree in...
There we go. That makes much more sense. There's a lower error rate. Huh.
the same way that we did for the original tree.
That's it? That's how you do it? That's so easy.
So now we get a simplified version of the original tree that we expect to have a better overall error rate on new data points. One question you might have is, maybe this tree is too simple for you.
Maybe this tree is too simple for you.
Default values in R for the tree function
I love simplification because I'm not smart.
are to continue splitting until each leaf contains 5 observations or more, and to stop splitting a node if the deviance, or error rate, goes below 1% of the deviance of the root node. But there are some cases when you might want to change that. You could do that using the tree control function, which goes inside the overall tree function as part of the control argument. Here, I've set up the tree control with 208 observations, the number in our overall dataset, which matches the dataset that we're looking at here, so not focusing on the training set now. The minimum deviance equals 0, So this tree will create a split whenever there's a change in the deviance, whenever we can improve the deviance. And min size equal to 2. That means that even nodes that only contain 2 observations are possible candidates to split. So the leaf nodes could contain only 1 object. That means that this particular set of arguments will produce a tree that perfectly classifies all of the data in our original data set. As is not surprising, we get a much more complicated tree this way. This tree is also likely to have a much higher error rate on new data points because it's probably overfit to our current data set.
Makes sense. I guess, I think. I feel like it had, like, this is too easy. I feel like it's not over yet. Because now we need to know how to assess it, right? Like, using bagging and boosting. Oh yeah, they tend to be changes in the data or in the variables included. For example, the dataset shown on the left results in this shown on the right, but if we change one data point, there is a high variance in the model and can result in poor accuracy when predicting new bagging and boosting are 2 ways to reduce the effect of this limitation. Ah, there we go. So we found a cross-validation of finding the correct pruning process, but that's not really it. Now we need to, there's like 3, like, so this process is interesting when you're doing decision trees. First, you create a tree. The first step of optimization is pruning the tree. The second optimization is minimizing the variance when new data is arrived, so bagging and boosting. I like this music. It's my favorite song. Reduce the effect of this limitation. At each step in the construction, we choose the split that provides the greatest reduction of MSE. Or Gini index. So, okay, first prune. Number 2, apply Gini index or cross entropy to minimize the error. And number 3, bagging and boosting to minimize the variance if there's new. So decision trees is a very fickle algorithm. Number one. We choose a split that provides the greatest reduction in MSC, gene index across entropy. Number two, pruning the tree. Number three, bagging and boosting to reduce the variance of new data coming in. Other methods perform better when there are linear relationships or complex interactions. How do I check if my data is linear? Bagging stands for bootstrap aggregation. The idea is that by taking the average of estimates from many models, you can get a composite model with lower variance than any of the original models. In the average of estimates from many models, you get a composite model with lower variance than any of the original models. Bagging can be applied to many different data mining algorithms, but it's especially effective when applied in the context of decision trees. Okay. Well, hold on. How do you use the Gini index or the... Is that already built into the... Or cross entropy? How do you know? Alright, I'm confused, man. Like, it told me what to do, but let's see here. Maybe... I think they made this way too simplistic. Index. How come I have a bad feeling that I need to read more about this. Chapter 8. All right. To motivate regression, she's okay, blah 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 blah. Like, she rarely talks about. Is there a Gini index? Yeah, here we go. Classification tree. Here. In an order to read results, we are interested not only in the class prediction corresponding to the direct operation, but also the class proportion. The task of growing the classification tree is quite similar to the task requiring the regression, just as in the regression use recursive binary. Recursive binary. Oh, the classification. Turns out the classification error is not sufficiently sensitive for tree growing, and in practice, two other measures are preferable. The Gini index, a measure of total variance across the K classes. It is not hard to see that the Gini index takes on a small value if all the PMKs are close to 0 to 1. For this reason, Gini index is referred to as a measure of node purity. I'm so confused what this fucking thing means. one can show that the entropy will take on a value near 0. When building a class tree, either the Gini index or the entropy are typically used to evaluate the quality of a particular split. Either the Gini index or the entropy are typically used to evaluate the quality of a particular split. Since these two approaches are more sensitive to node purity than is the classification error rate. Any of these three approaches might be used when pruning the tree. When pruning the tree, but the classification error rate is preferable if prediction accuracy of the pruned tree is the goal. If he means by classification error rate, when we did our cross-validation, is that what you mean? These data contain a binary outcome HT for 303 patients. An outcome of value best indicates that the heart disease is based on. There are 13 predictors, including age, sex, and cholesterol. In our discussion thus far, we have assumed that the predictor variables take on continuous values. We have assumed that the predictor variables take on continuous value. Yeah, I know. However, decision trees can be constructed even in the presence of qualitative. I know. Okay, yeah. So they did use cross-validation. This is the... Is this what they mean by classification error rate? The natural alternative to RSS is the classification, since we plan. However, in the classification say RSS cannot be used as a criterion for making what a natural alternative is the classification error rate. Since we plan to assign an observation against the most commonly occurring class, the classification error rate is simply the fraction of the training observation. Okay. Is simply the fraction of the training observations in that regions that do not belong to the common class. Okay. I think I know what that means. It's this horse shit right here, probably. I think it's this thing right here, the table thing right here. This is the classification error rate. The 8 plus 7 over 7 plus... Okay, I get it. I mean, in R though, will it show the Gini? I mean, we have CV tree, right? So C9 is the cost complexity and pruning. Why are we using cross-validation? Okay, we're using cross-validation. So does within cross-validation? Okay, when you're doing tree. How does it know how, like, I don't really get the whole Gini index thing. I don't get it. I mean, I get it, but I mean, I get what it's saying, but so do we not calculate the Gini index at all, or cross entropy when pruning the tree? But we use cross validation. Why? Why? This seems like a thing that we have to do. It feels like a hyperparameter in my opinion. Fuck it, I'm gonna email my old teachers. What are their names again? Craker and Brisbane. I had to email my old teachers that I haven't spoke with in a long time. Okay, I think I'm done. Although we haven't really physically worked on the Pokemon dataset, we did learn a lot about classification trees. The only thing that I'm still confused about is the Gini index and cross entropy. And how does it optimize the quality of the split? Even though the split does not reduce the classification error, it improves the Gini index and entropy, which are more sensitive. For instance, consider the split near the bottom right of the brown prim tree, regardless, is predictive for both those options. Why then is the split performed at all? The split is performed because it leads to increased node purity. That is, all 9 of the observations corresponding to the right-hand leaf have a responsibility, whereas 7 out of 11 of those. Why is node purity important? Suppose that we have a test observation that belongs to the region given by the right-hand leaf. then we can be pretty certain that its response value is left. Wait, suppose that we have a test observation that belongs to the region given by the right-hand leaf. Then we can be pretty... Why is the node period important? Suppose that we have a test observation. Why can't I comprehend this sentence? We have a test observation that belongs to the region given by that right-hand leaf. And then we can be pretty certain that its response value is yes. In contrast, if a test observation belongs to the region given by the left-hand leaf, then its response value is probably yes. But we are much less certain. I hate the fact that I still don't understand this. So it's just a means of... I gotta Google it, man. I don't know. Okay, I'm done for the day. I'm so tired right now. It's already 1:30. I'm done. Thank you, everyone.